Okay, hello all and welcome back to another video. Today we're going to be going over the 1999 free response questions for AP Physics E Mechanics. E&M videos to come soon when I learn the rest of it. No, I'm just joking, but they will come eventually. But let's just start. So in a laboratory experiment, you wish to determine the initial speed of a dart just after it leaves a dart gun. The dart of mass m is fired with the gun very close to a wooden block of mass m naught, which hangs from a cord of length L and negligible mass as shown above. Assume the size of the block is negligible compared to L, and the dart moving horizontally when it hits the left side of the block at its center and becomes embedded in it. So the block swings up to a maximum angle theta max from the vertical. Express your answers to the following in terms of m, m naught, L, theta max, and g. Okay, so question 1a. Let's just write question. Why can't I? Question 1a. Determine the speed v naught of the dart immediately before it strikes the block. Okay, so we know that we want to find v naught, but we can figure out v naught from the final velocity the block attains, which we can figure out the final velocity the block attains from energy, right? So we're going to start with just conservation of momentum because we see in the problem that it says it becomes embedded in it. And after it's embedded, they both swing up as a system to a maximum angle theta max. So we're going to start with our conservation of momentum equation. So P final equals P initial. And we're going to say, what's the initial momentum, right? So the dart, only the dart with mass m and v naught is the initial momentum because the block of mass m naught was not moving, so it won't have momentum, has to equal the final momentum of the two as a system. So we're going to say m plus m naught. Because it becomes embedded, this is an inelastic collision, and I'm allowed to use conservation of momentum because the two stick together, right? So momentum has to be conserved. But m plus m naught is the two as a system that move together with a velocity final v, right? You could write it with individual momentums, but this will be what it simplifies to. I'm just skipping that step. So let's solve for v naught. So v naught equals m plus m naught over m times v. Right. So this velocity is the velocity that the system attains once the two, so that's the dart, if you don't see that. But once the two are embedded and moving, so this is v, right? So that's the final velocity of the two. Well, what's the final velocity of the two? So we're about to figure that out over here. Oh, great. There's a lot of space. So what we need to think about is this theta max enables us to find a height h that the block travels to. So once it's here, when the block's here, right, it has some kinetic energy k. But once it swings up over here, it has only gravitational potential because this is a pendulum, right? And it's a simple harmonic oscillator in which at this point it's at its maximum theta. Because it said theta max, that means it has no velocity. It's about to start swinging back down, right? So it can only have gravitational potential. So we have to say conservation of energy because there's no external forces. We're going to say E final equals E initial. We're going to say K initial equals UG final, right? And now what I want you to think about is how are we going to figure out this UG final, right? Because UG is the total mass times gravity times h, right? I'm not even going to write the second part. Actually, I will. So we're going to think about this h in a second, but the k naught is 1/2 the total mass plus the final velocity of the two block system squared, the final velocity after the collision, right? So this v is the same as this v. I just want you to see that so that we can make some connections later in order to find v naught. So what you need to realize is that this h, we don't have it. We have to derive it, right? So I'm going to draw that triangle. So here's length L. Here's length L, right? And after length L is here, but there's this little, length L is also here, right? Because the length didn't change, it's just swinging. So I'm going to actually switch colors to point this out. There's this other length I'm going to call A, right? And that A corresponds to this right triangle. And here theta max is created. Oh, I can't even write theta. I have to lower this. So here theta max is created. So theta max is related to, how can we relate A and L in terms of theta max? So we're going to say cosine of theta has to equal, I'm going to keep this like this, A over L, right? So that means L cos theta is equal to A. So A is just this little distance in red, right? But I'm also going to draw something in yellow. This is the H. Now, if you see here, this little distance is the same as that distance, H. That's the height that we're trying to find after it swings up. So logically, if we look at this, wouldn't it make sense that L minus A would give me the height H that the block swings up to, right? The gravitational potential energy it gains. It does, right? So let's say L, and A was L cos theta. L cos theta is equal to that H that we wanted. I'm going to make this H just, so these are the same H's, right? So now I'm going to simplify this a little bit, factor out L, so this becomes 1 minus cos theta equals H, and that part's done. So now I'm going to go back to my equation up here and sub in H, but first I'm going to cancel these MTs. MT is just the mass total, the total mass of the system, which is this M plus M naught, right? But they're on both sides, so I can just cancel it. So I get V squared over 2 is equal to G, and remember H was L1 minus cos theta, L1, oh, that's too many parentheses, G L1 minus cos theta. And now I'm getting closer to V in terms of what I have. M naught, L, theta max, and G. That's what I'm allowed to use. So I'm going to keep solving. I'm going to say V squared equals 2GL 1 minus cosine theta. Now I'm going to solve for V by square rooting, or taking the root, 1 minus cos theta. Done. So now I can plug this back in up here and find what my V naught is. So I'll just do that. And it's really not a tedious process. It's just rewriting. So V was square root 2G L 1 minus cos theta. So this is the initial velocity in terms of all the given quantities. So that's the answer to question 1. Let's move on to question 1, part B. Here's part B. So let's see, the dart and block subsequently swing as a pendulum. Determine the tension in the cord when it returns to the lowest point of the string. Okay, so what we need to realize is that after it attains this maximum gravitational potential energy, that gravitational potential energy will turn right back into kinetic energy, just in this way. Well, kinetic energy has no vector, right? Just the velocity will be in the other way, correct? Because a simple harmonic oscillator, it kind of goes like this, back down here, then it swings this way, and it repeats. It cycles through all that again, right? So if the kinetic energy at the bottom is the same, then the velocity at the bottom must be the same. So we know that that velocity at the bottom must equal square root 2GL 1 minus cos theta. But why do we care about the velocity at the bottom? Well, I'm about to show you, because if we recognize that this is a pendulum, we realize it's undergoing uniform circular motion, right? So our equations for uniform circular motion, we're going to think about it. We're going to think about which ones we're about to apply. So let's draw our free body diagram, because if we do a sum of forces, we can relate centripetal acceleration to velocity. So force tension has to be up, and that has to be greater than force gravity, just because the pendulum is going to start moving up in a bit, right? So I'm going to write my Newton's second law. Some forces Y has to equal force tension, which I'm going to call this my positive. This is my negative. Minus Fg, which is down, has to equal the total mass plus the centripetal acceleration, because the centripetal acceleration is the acceleration in the radial direction. And if we draw this out again, the acceleration is that way. That's centripetal acceleration towards the radius, towards the center, right? So now let's sub in some things here. So force tension, well, let's solve for force tension. Knowing Fg is mg, we can write mt G plus MT AC. So that's our force tension. But what is AC? Well, on your equation sheet, you should see AC equals V squared over R. In this situation, our radius is L, so AC over V squared over L. But we know this V at the bottom was this entire equation, 2GL 1 minus square root, right? But if I square a square root, right, if I square whatever's in here, square root, that will just give me whatever's on the inside by itself, because these two cancel one another. So I'll ignore the square root. I'll just write 2GL 1 minus cos theta over L equals the centripetal acceleration. Well, these L's cancel, so my centripetal acceleration is actually 2G 1 minus cos theta. So now I'll plug that into this equation, and I see MT is in both of these expressions, so I'm going to factor it out as well. So I apologize if I'm moving a little fast. You can slow down the video. But, yeah. So G plus, and our centripetal acceleration was 2G 1 minus cos theta. So let's see. 2G 1 minus cos theta. So right here, now I'm getting closer and closer to my final expression, right? So MT was M plus M naught, and so I'm going to write that out fully because that's what the College Board wants. M plus M naught. And I see there's G's here that I can factor out, right? So I'm going to go ahead and factor that out. So I'm going to factor out a G. So I'm going to say 1 plus 2 times 1 minus cos theta. And I'm going to expand that entire expression. So I'm going to say M plus M naught times G. It's going to be 1 plus 2 minus 2 cos theta. And this gives me the final force tension, which is equal to M plus M naught G 3 minus 2 cos theta. And that seems like a lot of work to get there, and it is. But yeah. All right, let's move on. So C. Let's see C. Let's see part C. I should zoom in here. So at your lab table, you have only the following equipment. That's a lot of equipment. So meter stick, protractor, stopwatch, set of known masses. Oh, a spring, great. So without destroying or disassembling any of this equipment, design another practical method for determining the speed of the dart just after it leaves the gun, indicate the measurements you would take and how the speed could be determined from these measurements. So with this, I'm really not going to say all the answers. I'm going to pick one that's the easiest. So I'm going to say use the spring to use the spring to calculate V naught by, am I using all the bit? Oh, wow, I'm not. To calculate V naught by shooting the dart at it and have the two stick. Use use the meter stick to measure compression. Utilize US equals, so this is just a conservation of energy, to find V naught given a known spring constant. I hope that makes sense. Right, so basically, they're just going to shoot the dart at a spring, whatever distance that spring compresses. Given a spring constant, you'll just set up 1/2 mv naught squared equals 1/2 kxc squared, and then you can solve. Let's move on to the next question. Part D, let's see. The dart is now shot into a block of wood that is fixed in place. The block exerts a force F on the dart that is proportional to the dart's velocity v and in the opposite direction. That is, F equals negative bv, where b is a constant. Derive an expression for the distance L that the dart penetrates into the block in terms of m v naught and b. Okay. So what we need to realize here, when I see this, I think impulse, right? So we're going to think impulse as well. So there's a couple little neat ways around this, but you should have learned this in class. I didn't. The first time I saw this, I had no idea what I was doing, but that's why I'm here. I'm teaching it so that you guys won't have the same mistakes. You'll be able to learn, be able to succeed on the exam. So knowing that the force varies with velocity, right? We're going to say F, we're going to write this down. F equals negative BV, right? But V has an implicit relationship with T, so this exists, right? This does exist. I'm just not going to solve for it. You can. I'm sure you've learned the differential equation in class, but that's not what we're going to do here. So we're going to use impulse, right? So impulse is the change in momentum by the impulse momentum theorem, which is the integral from time 1 to time 2 of force dt. So what we need to realize, we need to pick our time 1 and time 2 carefully. So the time 1, we're going to call that 0. We're going to say the integral from 0 to infinity, right? So I'm going to draw this out. We're going to say 0 to infinity. Why? Because as the dart infinitely approaches L, on the graph of the velocity time graph, it looks kind of like this. It will never hit 0. The velocity will never hit 0. But we know physically that block can't continue to keep going. It'll stop at some point. It'll cross this axis at some point, but this equation is telling me no, it won't. So we're going to go from 0 to infinity, and we know that as it approaches that infinity, the length that it travels, which is this y here, will be L, right? So knowing that, so we're going to take the integral from 0 to infinity of negative bv, because that's f dt, right? That has to equal the change in momentum, which is momentum initial, oh no, sorry, momentum final minus momentum initial. Well, the momentum at the end, it has to be 0, right? Because it stops. It eventually stops. So the momentum initial has to be negative mv naught. This negative just translates here. So mass times the initial velocity of the dart has to equal, and I'm going to take out my constants from my integral. So 0 to infinity of v dt. Right. So now I'm going to cancel these negatives, and I'm going to move b over here by dividing. So I'm going to say mv naught b has to equal the integral. And now v, I'm going to use a little trick here. Dx dt is v, right? This is common knowledge. But if I realize that if I take 0 to infinity of dx dt times dt, these dt's cancel. That leaves me with mv naught over b is equal to the integral from 0 to infinity of dx. So integral dx will give me the function x as a function of time, right? But I need to realize that as I approach t equals infinity of x of t, like I drew up here, that x of t will approach L, the distance at which the bullet lodges. So I'm going to rewrite this like this. mv naught over b is equal to the integral from 0 to L dx. And that gets me mv naught over b equals L. That's my final solution. So this is just I'm sure they won't test this on the upcoming 2025. At least I'm pretty sure, but it can show up, right? Because the indefinite integrals are really like a touchy subject with physics. Because with calculus, you have to do the limit, like you say 0 to b, you do limit as b approaches infinity. This is really more conceptual calculus, but it's still the same calculus, right? This College Board awards a point for recognizing that as time goes to infinity, the distance goes to L, right? So let's go to that next page. So MV not B was our answer. So let's go to question 2. Okay, so question 2. Oh, I love this question. A spherical non-rotating planet of radius r and uniform density rho throughout its volume. Oh, has a uniform density rho throughout its volume. Suppose a narrow tunnel were drilled through the planet along one of its diameters, as shown in the figure above, in which a small ball of mass m could move freely under the influence of gravity. Let r be the distance of the ball from the center of the planet. So when they say that it's a narrow tunnel and they don't give us a radius of the tunnel, that means it's negligible, not non-negligible. It's negligible, and we can treat it as if it's just a sphere, because it says aspherical, right? So question 2, part A says, show that the magnitude of the force on the ball at a distance r is less than r from the center of the planet is given by F equals negative CR, where C is 4 pi or 4/3 pi g rho m. So here we're going to apply, this is unit 2, right? This is a unit 2 question, gravitation. We're going to apply the idea that rho equals mass over volume. So that rho ratio will not change no matter what. So I know I'm going to visualize this. If I'm at a distance, here's r, here's my center, here's r, then only the mass, sorry, only a portion of the mass will affect me, right? Whatever, oh my gosh. So this section of mass will have an equal pull on the ball, the little ball of mass m, because it's enclosed by it. So that mass won't matter. I only care about this m prime in the middle, right? So understanding that, we need to find m prime in order to plug it into our equation for gravitation, Newton's law of gravitation, right? So I know that that ratio will be m prime over volume prime. So this ratio is the same. They both have to equal each other, which equals rho. So what is volume prime? Well, volume prime is the volume of that little radius that we need. It's this, I'll draw it again. Little r, big R was out here. We want little r. We want this little volume in order to find the ratio of the masses, in order to find m prime. So that's going to be 4/3 pi little r cubed, right? Not big R. So now knowing that rho equals mass prime times volume prime, shouldn't, then that means rho volume prime equals mass prime, right? So that's going to be rho 4/3 pi r cubed equals mass prime. So why did we find mass prime? To use it in Newton's second law of gravitation. So the force of gravity is going to equal negative gm over m prime r squared, little r squared, mind you, because the mass that we care about, this little mass, the center of mass of that little mass, we're going to treat it as if it's all there at a distance r, little r, right? Little r, not big R from this other mass. So here's m, that's that m. And the center of mass is where we're going to treat all the mass to be at m prime. But all the other mass that is not a part of m prime has an equal pull by Newton's shell theorem, right? It's like the electric field inside a conductor is zero. It's kind of the same idea, right? So I'm going to sub in my m prime here. And the reason why this negative is here is only because the College Board says so. Normally it'll be positive. This just matters where you define negative and positive. I'll explain it later why they put a negative instead of a positive, and it'll hopefully make more sense. So g little m times, well, we said m prime was 4/3 pi r cubed rho over r squared, right? So r squared and r to the third divided by r squared just leaves me with r. So I'll rewrite that as gm 4/3 pi r rho, right? And they want c to be 4/3 pi g rho m. I can take my c, so here all of these g rho m, all of these belong to c except for r. So I'll say c r equals f. Circle that. So College Board really just wants to see this part of it. They want you to understand Newton's shell theorem and understand that the only mass that has the pole is m prime, not the other mass that is enclosing that little mass, right? So I shouldn't circle it like that. Sorry if you can't see that now, but yeah. So I'm going to say negative CR equals F. So on the axis below, sketch the force F on the ball as a function of the distance r. So I don't have that graph right here, but I'll try to replicate it to the best of my ability. F 0. We'll just call this r. I don't care about the rest. So here's what they want you to understand. Knowing this equation that F equals negative CR, they want you to not put anything up here. Do not, like, because they defined it to be negative. They're telling you, hey, draw negative because we're saying that the force is negative. So understanding that this is a linear relationship where C is a constant, right? 4/3 is a constant, pi is a constant, g is a constant, rho and m are constants. So this is a linear relationship that's decreasing, and all you have to do from 0 to r is draw like that, right? Because for those, it's only going to be a linear relationship. For r is less than r, it's going to be a linear relationship, and after that, from that point on, the r squared effect is starting to kick in, right? Because no longer does this CR equation apply? Oh, oops. Does that CR equation apply? No, we're going to use Newton's gravitation. Of the full planet's mass, we're going to use this equation where r squared actually affects it. And the inverse square relationship is like this. And how did I get this graph per se? You kind of just have to memorize that 1 over r squared yields something that looks like this. And to reflect it to be negative 1 over r squared will yield something like this, right? So that's my graph. I can move on to the next question. So linear from here because r is less than r, and then the r squared effect kicks in after because all the mass can be treated, because here's r, all the mass can be treated as the center, to be at the center, right? Let's go to the next question. So the ball is dropped into the tunnel from rest from at point P at the planet's surface. Determine the work done by gravity as the ball moves from the surface to the center of the planet. Okay, so what they're kind of baiting us to do here, was that question B? Yeah, here's B. What they want us to do here is they want us to use the work integral, right? Because negative CR is not a constant force, right? That's not constant. It's not constant. So we know that if we have varying force, then we need to find the area under the graph to find work. The area under the graph is the integral. So we'll use the work integral. And what are our bounds? Well, from what distance do we go to? We go from big R, right? Because if I draw this out, here's the center. We're going to go from big R to 0, to where R equals 0, right? So R, 0 of the force, which is negative CR, ER. Well, if you're asking, well, isn't the work integral from 0 to x f dx? Why did you put dr, right? It is, right? I just subbed in my f here to give me negative CR, and because we have coordinates that aren't in terms of x and r, I kind of just replaced it with r. You're allowed to do that, right? So now I know that by calculus, I can make this a negative integral from 0 to r just to make this easier for me, of negative CR dr. These negatives cancel, giving me the integral from 0 to r CR dr, yielding CR squared over 2, 0 to r. Now that gives me C big R over 2, C big R squared over 2 equals the work. Okay, that question's done. Ooh, running out of space. So let's see, part D. I'll lower this so I can have more space. So part D asks me, determine the speed of the ball when it reaches the center of the planet. So when they just asked me to solve for the work, it's because they were setting me up for this next question. So what you need to understand is work equals the change in kinetic energy, right? Well, you might be thinking, hey, isn't there like gravitational potential energy? No. In this situation, there isn't because we physically took it out of the system by saying the work done by gravity is the change in kinetic energy. Otherwise, you would say that the change in gravitational potential energy, or well, the gravitational potential energy turns into kinetic by putting gravity back into the system. But here we're saying we're taking it out by saying that the work done by gravity is the change in kinetic energy, right? So it's really just messing with the system, right? So now we're gonna think work equals the change in kinetic energy. Well, the change in kinetic energy is K final minus K initial. So the K final, it says the ball is dropped into the tunnel from rest. So from rest means K final, sorry, K initial is 0. And we solved for the work earlier, so we're going to write CR squared over 2 equals 1/2 mass of the ball and the final velocity of the ball. We have 1/2 on both sides, so we're going to cancel that. And we're going to solve for V final squared. So CR squared divided by M, take the square root, gives me V final. That's done, right? So now E is an interesting question. I like this. So fully describe the subsequent motion of the ball from the time it reaches the center of the planet. So from when it reaches the center of the planet, what happens after is what they're asking, right? Because it came from here, it went here, right? But now what happens after that? That's what they want to know. So the ball will continue to travel to the opposite end of the planets until negative p, negative point p, right? Because it travels to negative point p, then returning to the center, then back to point, then back to point P, like a simple, oops, like a harmonic oscillator. So, in other words, it will oscillate from P to negative P. So what they want you to realize with this question, they're kind of baiting you into thinking, okay, this is simple harmonic motion. This entire like mechanism is representative of simple harmonic motion. And earlier I said I'll explain why the negative's there, and I'm about to do that now. The reason why the negative's there is because the negative serves to show that it's a restorative force that's acting on the ball that varies with position, right? Because the conditions of simple harmonic motion are that force is opposite and proportional to the displacement, which it is here, right? So if you think of the spring equation, negative kx, if you think of, uh, if you think of the torsional pendulum, negative k theta, that's the torque, the restorative torque, those are opposite and proportional to the displacement, as is this. This is what they want you to see. That's why they put the negative there. It's arbitrary, right? And that baits you to find the solution for f. So f is write an equation that could be used to calculate the time it takes to move from the ball to at, to move from point P to the center of the planet. It is not necessary to solve this equation. So since you now know that it's simple harmonic motion after answering E, you know that I'm going to draw this out. So the time it takes to move from point P to the center is 1/4 an entire period. Because it will go here, so here's 1/4, and it'll go here, here's another fourth, but now it'll come back. Here's another fourth, and that's another fourth. That's one entire period, one entire full oscillation. Well, one entire full period cycle, one full cycle. So if you understand the differential equation of simple harmonic motion, you really need to understand that d2x over, well, in this situation, x is r. d2r over dt squared has to equal negative w squared r, right? Well, if you understand that this is the acceleration, then you can understand that the restorative force, which we'll use some forces, equals ma equals negative cr. You can say that's equal to negative c over mr, right? So that means w equals c over m, right? Now, College Board gives you the option to leave it in this form where it's negative c over mr, and you can solve this differential equation. But what I would recommend doing, just to ensure the point, is to say, okay, if this is my w, period equals 2 pi divided by w, or this is w squared, right? So w has to equal square root c over m. So that gives me the period to be 2 pi m over c. So this equation can be used and then solve for 1/4 t. And that's it. So this is a simple harmonic motion question, right? And this is the equation that you could use. Understanding that A is d2r over dt squared, and then plugging in what A is in order to find R as a function of time, and then you can solve it like that. So that's two ways to do it. Now let's see the next question. Okay, so Mech 3, this is the third, is this the fourth page? Wow, I'm running out of space. This is the third and last page. So, as shown above, a uniform disk is mounted to an axle and free to rotate without friction. A thin uniform rod is rigidly attached to the disk so it will rotate with the disk. A block is attached to the end of the rod. Properties of the disk, rod, and block are as follows. So the disk has mass 3m, radius r, moment of inertia id 3/2 mr squared. Oh, okay, so they solved it for us. So these are the inertias we have. We don't need to calculate anything else. So the rod has mass m and length 2r. So its center of mass is like in the middle because it's a uniform rod. And the block has mass 2m. Okay. And it has no radius, so it's like a negligible, it's a point mass. So the system is held in equilibrium with the rod at an angle theta naught to the vertical, as shown above. So it's that way. Express a horizontal, okay. By a horizontal string of negligible mass with one end attached to the disk and the other to a wall. So this is like tangent at like 90. So express your answers in terms of m, r, theta naught, and g. So the tension. So this is a rotational statics problem. So I'm going to start by saying some torques equals 0, right? Because it's not moving. And I'm going to write out my torques. So now I'm going to use my right hand rule. So the torque due to gravity from the center of mass of the rod is at r. So I'm going to say torque, and it's positive because it's counterclockwise. So torque due to the force gravity of the rod, and I'm going to add that with the torque due to the force gravity of the block, which also produces a counterclockwise torque, FGB, minus the torque due to the force of tension, which all has to, I wrote 0 twice, but it doesn't matter. So now I can rearrange this and say that the torque due to the, oh my gosh, I wrote that horrible. Torque due to the force gravity of the rod plus the torque due to the force gravity of the block has to equal the torque due to the force of tension. So now let's plug in each of these, understanding that tau equals r cross f, which is equal to r f sine theta. Let's do the tension force first. So at what radius is the tension force? Well, it's at a radius, which is the radius of the disk, which would be, ooh, I gave myself like no space, which would be r force tension, and the sine, it's tangent to the disk. So we'll say sine 90 degrees, which is just 1. So now the torque due to the force gravity of the block is a little bit harder um, because if I visualize this, here's the block and here's theta naught. So the force gravity pulls down like that. So I'll really have to say that the theta between this, theta between, which is what we want, because we want sine of theta between, is sine of 180 minus theta naught, right? Because this entire thing is 180. If I subtract that little portion, that's theta naught right here, that'll give me the angle between. So that's sine theta, because sine theta, theta naught actually, sine 180 minus theta is sine theta naught. So because both of these forces pull down, they'll have the same sine theta. So I don't need to do that process again. So I'll do the force of the gravity of the block first. So 2r, and the block pulls down with a force. What was the block's mass? So times 2 mg. Oh, I have like no space. We'll zoom in really, really close. Sine theta naught plus, and then the torque due to the force gravity of the rod is at just r, because it's at the center of mass of the rod, r, the mass of the rod, which was mg sine theta naught. Now I'll combine like terms. 2 times 2 gives me 4. 4 plus 1 is 5, so I'll get 5 mgr sine theta naught is equal to rft. Cancel my r's and say ft equals mg sine theta naught times 5. Great. Force tension done. I have space. Oh my gosh, I have so much space over here. Section that off. Okay. So now determine the following for the instant immediately after the string is cut. So the magnitude of the angular acceleration of the disk. Okay, so the magnitude of the angular acceleration of the disk after the string is cut, now some torques is no longer 0. It's I angular acceleration. Say this is Bi, right? But now the torque due to the force of tension is disappearing, right? So the sum of torques is just the torques produced by these two, which we understood was 5 mg sine theta naught times r. But you might be saying, wait, wasn't that the tension, or wasn't that the torque due to the tension in the string? It was, right? But now that the string's cut, at that instant, because the torques due to the rod and the block had to be equal to the tension of the string, that means if they're equal, then they have the same like numerical values or like representations with these numbers. Because if you think about it over here, we said we just added these. This is the torque due to one. This is the torque due to the other. That gives me 5 mgr sine theta naught, right? So now this is the torque that we have. Well, what's our I? The I of the system, we have to sum the moment of inertia. So sum I equals I system, which is equal to, and they gave it to us. They gave some of them to us. So the I of the disk is 3/2 mr squared plus the I of the rod about one end, 4/3 mr squared. And the block can be considered a point mass because we didn't get a radius for it. And that will be 2m, and that's at 2r squared, which will be 4r squared or 8mr squared. So now we'll convert these fractions into something we can actually use. So I'll convert them into 96mr squared plus 12. No, not 12. 6mr squared plus, what's 8? We'll say 48 over 6mr squared. Now we add all of these numbers up in Desmos because I don't like doing addition. 65. So 65 over 6m r squared equals I total. Now we can use Newton's second law. So they want the angular acceleration, right? Yeah. So we'll say 65 over 6m r squared times angular acceleration equals 5 mg sine theta naught r, right? So 65, 6, I'll cancel r's, and this is r to the first because r squared divided by r gives me just r. Angular acceleration, 5 mg sine theta naught. Now I'm going to divide by 65, 6 mr squared on both sides to get angular acceleration by itself. And I'll get 30 over 65. Well, the m's cancel. G sine theta. All right, this is not r squared. It's just r. G sine theta naught divided by r. And we'll simplify that down to, what's 65 divided by 13? So 6, 13r, g sine theta naught. That is the angular acceleration. Amazing. Let's do the next part. I. Magnitude of the linear acceleration of the mass at the end of the rod. Okay, well, we know since this is a rigid system of objects, they're all attached, that the angular acceleration of one has to equal the angular acceleration of the other. So r alpha equals a translational. So what's the r of the mass at the end? Well, that would be 2r. So 2r times the angular acceleration that we found earlier. Oh my gosh, that just does that sometimes. Times 6 over 13th r g sine theta naught. Right? Cancel the r's. 12 13ths g sine theta naught is my translational acceleration. Now for the final question, which is a little bit more annoying than the other ones. Let's see. As the disk rotates, the rod passes the horizontal position shown above. Determine the linear speed of the mass at the end of the rod for the instant the rod is in the horizontal position. So since we found the linear acceleration, we could simply just say, we're actually going to do it that way because it's easier that way. So we're going to use our kinematic equation because it's a constant acceleration. Or no, we're going to use the angular kinematic equation because it makes more sense. So we're going to say the final angular velocity squared is equal to the initial angular velocity squared plus 2 alpha delta theta. So it was at rest, so this one comes to 0. And now what's our delta theta? This is what we want to figure out, because if it was in this position with theta naught, and now it reaches, I'll make that dotted, this final position, which is theta final. Theta final, here was 90, so it rotates from here to here. So what's that angle? Well, that angle is going to be, sorry, I should really write a different angle. So we'll write beta. That angle beta is equal to, because this is a 90-degree angle, 90 minus theta naught. That's what it rotates through, right? So beta is the angle, which is delta theta. Beta equals delta theta, right? Which is equal to 90 minus theta naught. So we're going to say W final squared equals 2 alpha. And 90 in radians, we have to use radians because that's how all of rotation occurs. We're going to say pi over 2 minus theta naught, pi over 2 minus theta naught. And what was our alpha? We'll just pull that from over here, which was 2 alpha, 2, 6/13 r g sine theta naught, pi over 2 minus theta naught. And we'll take the square root of that to get W final. Now we know RW final equals V translational. So we'll multiply by R. So I'm going to say R square root, and I'm going to multiply all this out. I'm going to get 12/13 R g sine theta times pi over 2 minus theta naught is equal to V translational. Well, I know R is equal to the square root of R squared. So I'm going to put that in there, and I'm going to take out, wait, did I say 2? Quickly. The 2 is inside there. I don't know why I'm doing that. So I'll just resimplify this really quick. So 4 times 3, yeah, this is your final answer. Sine theta pi over 2 theta over 2 minus theta naught equals V translation. This is the correct answer. This is the correct answer. I apologize for that, because the 2 was in the square root because I took the squared root of this entire thing to find W final. So I hope that helps. Again, let me just do the same outro. I hope you guys do well in your exams. I hope this helped, and I apologize for that mistake. Thank you for watching.